Trig 3.4. These are linear and angular speed. Linear. Some sort of simple formulas that we can come up with. Linear speed is speed along a line, but it can be on the sort of the outskirts of a circle, here along the edge of a circle. So this is how fast a point is moving around the circle's circumference. So this speed, which we're going to call v for velocity, is going to be the distance over time. And the distance we measure around a circle is s, and time is going to be t. So linear speed, v equals s over t. Angular speed is when we measure not the point going around the circle, like this x is, but it's how a ray is sweeping this area going around the circle. It's how quick this angle is changing. That's the angular speed. The other one is how quickly this point is moving around the circle. But it's not, it's just the point itself. This one's the whole ray that's moving. We call that omega. It's a W with a little tail on it. And it is theta over t, the change in theta over t, the change in distance. So that makes sense. Now this can be degrees or this can be radians, but radians is a better unit to put it in just because you can do a few more conversions. Because this velocity, linear velocity, if that is s over t, and remember s, this is one that we should keep in mind, equals r theta. Here theta must be in radians. So s is r theta in radians over t. But hold it, this portion is omega. So this is r omega. And those three formulas this v equals s over t, omega equals theta over t. Theta can be in radians, but it doesn't have to be. But if it is, then we can say this r omega is the same as linear velocity. And that's sort of helpful. This is sort of that point. You need to get the angular velocity a certain distance away, and that's what that point is over here. So we need to work some problems that have these formulas involved. So we're on page 124, I hope. My gosh. Let me move this back. Page 124, number 4. These directions sound a little crazy, but it'll make sense once we draw a picture. Suppose that a point P is on a circle with radius r. So we're on a circle, radius r, and P is a point on that circle. And ray OP is rotating with an angular speed of omega. So this is moving at omega's angular speed. For the given values of r, omega, and t, find each of the following. We're supposed to find Angle generated by P in time t. This is that angle, say right here, that theta. So what are they giving us for this? In number 4, r is equal to 30. This is in centimeters. Omega is pi over 10. And this is radians per second. And t is 4 seconds. That's what t is. So, we need to find the angle generated, that theta generated by this. So which one of those formulas, let's see, S equals r theta, that has theta in radians. V equals S over T, or R omega, well, that doesn't have the radians in it, and omega equals the theta over T, and this can be radians. I'm going to put the R up there because I'm going to use radians all the time. So this is then, we've got omega, we've got T. We can figure out what that is. So part A. Omega, which is pi over 10, that equals the theta, which we don't know in radians, over the time, which we do know is 4 seconds. So I'll multiply both sides by 4, and we get 4 pi over 10 is that theta. This is in radians. Reduce, and you get 2 pi over 5 is theta. That's the first thing we're supposed to find. Part B, distance traveled by P. So we need the S. Let's see, S equals R theta in radians. Well, in those 4 seconds, it's gone through this angle at this radius, so that one's not so bad. R is 30 centimeters, by the way, and theta is the 2 pi over 5. So 5 goes once, 5 goes 6. 6 times 2 is 12 pi centimeters. That's what that distance is. And finally, they want us to find the linear speed, or v, which is s over t. We found s. That's 12 pi centimeters over t for seconds. This reduces to 12 over 4 is just 3 pi centimeters per second. So these little bitty formulas can find a whole bunch of information. I should have boxed this in also. Should have done it earlier. There's another formula. Since omega is theta over t, and s equals r theta, we can rewrite this, omega t is equal to theta. Plug that in for the theta. So s equals r omega t. With that formula, we can come up with some more things, like number 26. They give us S, 8 pi over 9 meters. They give us R, 4/3 of a meter. And they give us t is 12 seconds. All these units should also come out right when we do this. If the units come out screwy, distances are all just that linear, feet, meters, centimeters. The angles should be degrees per second, per minute, whatever. The speed, linear speed, should be miles per hour, feet per second, inches, whatever. So this one should work out. Let's see. So S, which is going to be a linear distance, is the R, which is 12, times the omega. Oh, we don't have omega, do we? But we've got S. S is the 8 pi over 9. 12 seconds. And, let's see, T is 12 seconds. R is 4/3 of a meter. So these are meter seconds. But of course, the omega is in here also, which we don't know. So 8 pi over 9 equals, when you multiply by 12, this is really just 4 times 4, 16 omega. Divide both sides by 16. 8 pi over 9 times 16 is omega. See, 8 will go once and 8 will go twice here. So we know that pi over 18 is omega. And the units should be, I guess since we did this in radians, this is radians per second. So these are some examples. Page, this is one example, I guess. Page 125. Number 40. There are several parts, but it starts with the Earth turns on its axis every 24 hours, and its radius 6,400 kilometers. Okay. They want to know the angular speed of the Earth in radians per day. The angular speed is omega in radians per day and radians per hour. Okay, so the angular speed is how quickly this is turning, right? How quickly theta is changing. So theta, if we want to do this in radians, is 2 pi radians in 1 day, or 2 pi radians in 24 hours. Well, this first one certainly is just 2 pi radians per day. But we can reduce this next one, pi over 12 radians per hour. Then they want to know the linear speed at the North Pole. Or South Pole. Well, that's got to be 0 because you're not moving. You're just spinning around in one place. That one's maybe too easy. But maybe that's to bring up. What's the linear speed at the equator? Well, let's see. That's this point moving around in 24 hours. So if we know that omega in hours, we can find the linear speed because we know r, we know omega. So r is the 6,400 kilometers, and the omega is the pi over 12 rad per hour. Let's see. We don't have to calculate that right now. Let's see here for part D. Linear speed halfway up the equator. So now we're looking at something with an angle of 45 degrees. And this will have a different radius. But we can figure that out because if this is the 6,500 or 6,400 and this is a 45 degree angle, then we can figure out this other one. Let's bring that picture sort of into just triangles. So this is maybe that doesn't make sense. 6,400 from the center to a pole. Also 6,400 from the center to the equator. This is a 45 degrees. We need this distance right here for the r. So let's see here. If this is 45, then this must be 45. And if I want that opposite side, and I know the I don't know the adjacent, but I can find this side maybe. Oh my gosh! If this is a 45 degree angle, then this must be right angle trig. We need that hypotenuse. This picture is a little misleading because this should be curved right here. That's part of a circle. But these 45s are the same. That means that this length and this length, which is the r that we need, are the same. So we know we've got a 45, 45, 90. This r is this r that we want is the leg for this 45, 45, 90. We know this is 6,400. So we have r squared plus r squared, or 2r squared, equals 6,400 squared. Or r squared is 6,400 squared divided by 2, and take the square root. So what is r equal to? And then we can figure out the circle that we're talking about and how quickly that point is moving. So we need to grab the calculator. Let's now put it over here. 6,400 squared divided by 2. Then we need the square root of that answer. This huge number here. So 4525.4834. .4834. That's what that radius is. And now we want the linear velocity, so v equals the distance s over t time. Well, it's still going to be an entire day, so that times 24 hours. And the The distance is the circumference, which is 2 times the pi, that number over there, 4525. Oh, let's see, 2 pi r. So we also need pi in here. My gosh, it's getting a little crazy. Let's bring our calculator back up. So I need really the 2 times the pi times the r, which is the answer I have up here, divided by the 24. So 1184.767. 7687. Let's put this down. So what is this? I'm going to put it here. 1184. Now, they've got all these numbers. I'm not sure which ones we should use. So I'm going to, because I'm running out of room, these are kilometers, and this is hours, kilometers per hour. So that's how fast you're traveling at the equator, 1,184 kilometers per hour. This can get really interesting and really confusing, but you should be able to do these problems. It'll take a little time, perhaps a little bigger sheet of paper than I've got showing here.